Hello dear students, welcome to physics classes. In previous video, we discussed about the image formation in the case of thin lenses. From that, we have studied how the image formation takes place in the case of thin lenses for different object distances. Now in today's class, we are going to discuss about the power of a lens. Dear students, we are using the lenses for some particular eye defects. And that lenses has some power which is recommended by the eye specialists. Now we will see what we mean by the power of a lens. In a simple words, power of a lens can be defined as it is the converging or diverging capacity of a lens. We know that convex lens which converges the incident rays of light and concave lens which diverges the incident rays of light. That converging or diverging capacity of that lenses is called as power of a lens. That is the simple definition. But in briefly, the power of a lens can be defined as the tangent of angle by which it converges or diverges a ray of light parallel to the principal axis incident at unit distance from the optical center. Now we will see briefly what we mean by power of a lens. To understand this definition, I am here consider one convex lens. Here I am considering one convex lens. Okay, and this is a principal axis of this convex lens, and this convex lens has exactly one central point. That central point is called as optical center. Now I am going to incident a ray of light, and that ray of light which is parallel to the principal axis. Okay, this is an ray of light which is parallel to the principal axis, and this incident ray of light has unit distance from the optical center. This incident ray of light has a unit distance from the optical center. That means unit distance means that distance may be 1 centimeter. Okay, that means it is the height of that incident ray of light from the optical center. That height or that distance is a unit distance. Unit distance means that may be 1 centimeter. Okay, and it hits at some point on this lens. That point I am taking as M. Okay, when it hits to this lens, then it will undergo the refraction. That means it will bend like this, and it will pass through the principal focus of this lens. Why it pass through the principal focus of the lens? We know that when we are going to incident a parallel ray of light on this lens, after refraction it will pass through the principal focus. But actually this parallel ray of light, incident parallel ray of light, should pass like this. Actually it should pass like this. But because of refraction, it will make some angle with its actual path. That angle I am taking as theta. If this angle of bending increases, then the power of a lens also increases. Understand? See here, this is an theta, then I can take this angle also theta, because these two angles are alternate angles. And we know that the distance from optical center to the principal focus is nothing but focal length. This distance is focal length. Then I can take from triangle MCF. Here I am getting one triangle. That triangle is MCF. So I can write it from triangle MCF. Tan theta is equal to, you know that tan theta is nothing but it is the opposite side divided by adjacent side. Here opposite side is H divided by adjacent side is f. But we know that this height is unit distance. So I can write if h is equal to 1, then I can write tan theta is equal to 1 by f. And this tan of angle, this tan of bending angle is called as a power of a lens. So that I can write tan theta is equal to P. That is nothing but the power. P is equal to 1 by f. This is tan of a bending angle, only a power of a lens. So that I can write P is equal to 1 by f. See here, the power and focal length of a lens is inversely proportional to each other. That means if focal length of the lens is more, then power of a lens is less. If the focal length of the lens is less, then the power of the lens is more. They are inversely proportional to each other. Now let us see about this one. Now here I am going to consider two convex lenses. This is the first convex lens. This is the principal axis of this lens, and exactly the central point of this lens is called as the optical center. Now I am going to incident a parallel ray of light like this. After hitting to this lens, this incident parallel ray of light will undergo refraction and it will pass through the principal focus of this lens. And this is an actual path of this lens. Because of a refraction, it will pass through the principal focus of the lens. Because I am going to incident here ray of light which is parallel to the principal axis. And it makes an angle theta 1. This is the bending angle. Okay. And here I am going to consider another convex lens. This is the another convex lens. This is the principal axis and central point is the optical center. Here also I am going to incident a parallel ray of light. After refraction, it will pass through the principal focus. This is the principal focus. And here the bending angle I am taking as theta 2. And we know that the distance from the optical center to the focus is nothing but the focal length. For first lens, I am taking focal length as f1. For second lens, I am taking focal length as f2. If you see, in two cases, the bending angle theta 1 is more than theta 2. Right? In first case, the bending is more. The bending of ray of light is more. In the second case, the bending of ray of light is less. So that I can tell theta 1 is greater than theta 2. And if you see here, the focal length of first lens is less and the focal length of second lens is more. And here I can write f2, focal length of second lens is greater than f2. Focal length of second lens is greater than focal length of first one. f2 is greater than f1. So I can tell from this equation, if the focal length is more, then power is less. See here, focal length of this lens is more, then power of this lens is less. And in this case, focal length is less, so that power is more. And here, the bending also more. If the bending angle is more, then the power also more. Here, bending angle is less, then the power also less. So that I can tell that from this equation, power and focal length of the lens are inversely proportional to each other. Okay. And another thing you should remember that the SI unit, the SI unit of power of a lens is is diopter. Diopter. It is denoted by letter capital D. This is the SI unit of a power of a lens. And we know that there are two types of lenses mainly. They are nothing but a convex lens and another one is the concave lens. We are calling convex lens as a converging lens and we are calling the concave lens as a diverging lens. For converging lenses, this power is always positive, and for converging lenses, for diverging lenses, the power is always negative. That one also you should remember. For converging lens, for converging lenses means convex lens. Power is always positive. Power is always positive. And for diverging lenses, that is nothing but a concave lens. Power is always negative. Power is always negative. Okay. And this power of a lens also depends on some other factors. Now let us see how the power of a lens depends on some other factors. And we know that the lens maker's formula. From lens maker's formula, we got one equation that is nothing but from lens maker's formula. From lens maker's formula, we got 1 by f is equal to n to 1 minus 1 into 1 by r1 minus 1 by r2. Right. Here 1 by f, we already know that 1 by f is nothing but that is equal to p. So that I can write 1 by f is equal to p. This power of a lens also depends on, see here, the refractive index of the lens and radius of curvature of the lens and focal length of the lens also. This is also very important. The power of a lens also depends on mainly three factors: focal length, refractive index and radius of curvature of the lens. Now let us see how it depends. See, this power of a lens is directly proportional to refractive index of a lens. If the refractive index of a lens is more, then power of a lens also more. So, if a refractive index is more, then power P is also more. Power of a lens also more. Okay. If a refractive index of a lens is less, then power of a lens also less. And another thing you should remember that if radius of curvature of a lens is less, we will observe radius of curvature of less in the case of thick lenses. See here, for thick lenses, I am considering thick lens here. Thick lens means the distance between the two surfaces of the lens is more. That type of lenses is called as thick lenses. For thick lenses, R is, that is nothing but the radius of curvature is less. R is nothing but the radius of curvature, that is less. And also focal length also less. F is less. If radius of curvature is less, then focal length also less, then power is more. They are inversely proportional, so power is more. So then I can tell that for thin lenses, if I consider thick lens, I am considering this is an principal axis, this is optical center, and this is the principal focus of this thick lens. For thick lenses, the radius of curvature is less. Radius of curvature is nothing but it is the distance from optical center to the any point on the surface of this lens. This one is less, and the focal length Focal length is nothing but it is the distance from optical center to the principal focus. This is also less. Then power of a lens is more for thick lens. For thin lenses, now we'll see for thin lenses. For thin lenses, this radius of curvature is more. See here, I am going to consider thin lens. This is an thin lens. This is the principal axis, optical center, principal focus. Principal focus here. Okay. This radius of curvature is more for thin lenses. R is more. R is more. R is more. And focal length of the thin lens also more. Focal length is nothing but it is the distance from optical center to the focus. This focal length also more. F is more. You know that if a radius of curvature is more, focal length is more, then power of a lens is less. So that I can write P is less. P is less. So I can tell that for thick lenses power is more, for thin lenses power is less. These all points you should remember. Okay. So that is about the power of a lens. Now we are going to derive one equation that gives the relation between the object distance, image distance and focal length. That one we will observe in the case of thin lenses. And this relation also we discussed in the case of mirrors also. In mirrors also we got one equation that gives the relation between the object distance, image distance and focal length. And that equation we called it as a mirror equation. But in the case of a lens, also we are getting the relation between the object distance, image distance and focal length. And that equation we are calling it as a thin lens formula. Now let us derive the thin lens formula. Thin lens formula. Now to derive this equation, I am going to consider one thin lens. See here, this is an thin lens. And this is the principal axis of the lens. And exactly the central point is called as optical center. Now I am considering an object which is placed perpendicular to the principal axis. That object is nothing but AB. This is an object placed perpendicular to the which is perpendicular to the principal axis. Now here I am going to incident a ray of light which is originating from some point on this object AB. I am taking a first ray of light incidenting on this lens, and that ray of light which is parallel to the principal axis. So this is the first ray of light originating from this object, and that ray of light parallel to the principal axis. And this one which hits some point on this lens, that point I am taking as M. Okay, that point M has some height from the optical center. Okay, it has some height H from the optical center. Then this incident parallel ray of light undergo the refraction. After refraction, it will pass through the principal focus. This is the principal focus of the lens. This is the first ray of light which is originating from the object. Now there is another ray of light which is originating from the object AB, and it will pass through the optical center. We know that when the ray of light pass through the optical center of the lens, then it will emerges out without any deviation after refraction, right? So here I am going to incident a ray of light which is passing through the optical center, and we will see there is no any deviation after refraction, right? This is the another ray of light. Then we will get the image of this object somewhere here. That image I am taking as B dash A dash. This is the image of the object A B. Right. See here, we'll mention the distances now. We know that the distance from optical center to the object, that distance is nothing but object distance. That one I am taking as U. The distance from optical center to the which one? Object. So here U is nothing but object distance. And we know that the distance from optical center to the image, that one is nothing but the image distance. So here distance from optical center to the image, that is image distance, I am taking as B. So B is nothing but image distance. And the distance from optical center to the principal focus, that one is nothing but focal length. It is a focal length. F is a focal length. Now we are going to derive the relation between the object distance, image distance and focal length of a thin lens. See here, we are getting the image of the object AB, and this image is nothing but which type of image is this image is a inverted image and it is a real image. Right. See here, from two similar triangles means, see here, ABC and A dash B dash C. They are similar triangles. In ABC, it will make angle 90 degree here. This is a right angle triangle. Here also, in A dash B dash C, it makes an angle 90 degree here. Right. They are similar triangles. So I can write from similar triangles. ABC and A dash B dash C. We know that in a similar triangles, the ratio of the side of the one of the triangle to the side of the another triangle is equal to the ratio of the base of the one of the triangle to the base of the another triangle. Right. So here also the ratio of the side of the one of the triangle, in the case of a triangle ABC, the side is I am taking as AB. So side AB of triangle ABC. Similarly, in the case of a triangle A dash B dash C, the side is nothing but A dash B dash. So the ratio is AB divided by A dash B dash. That is equal to the ratio of base of the one of the triangle. Base of ABC is nothing but BC. So that is equal to BC divided by base of another triangle, that is a triangle A dash B dash C. Base of this triangle is B dash C. Right. Divided by B dash C. This equation I am taking as equation 1. Similarly, I have another two similar triangles here. That one is nothing but MCF. Right, MCF. In MCF, here it is an 90 degree, and here another A dash B dash F. They are also similar triangles. So from another similar triangles, they are nothing but MCF and A dash B dash F. So here also we should take in MCF, the side is nothing but MC. divided by, in a triangle A dash B dash F, the side is A dash B dash. So A dash B dash, that is equal to, now we have to take a ratio of the bases of the two triangles. So for triangle MCF, base is CF, divided by, in the triangle A dash B dash F, the base is B dash F, so B dash F. But here the height MC is same as that of the height of the object, that is AB. So that I can write MC is equal to AB. In this equation I can write here MC is equal to AB because the heights are same. Then I can write this equation as, then I can write, instead of MC I can write AB divided by A dash B dash is equal to CF divided by B dash F. So this is an equation number 2. Now I can compare equation 1 and equation 2, because in the left hand side both the equations has AB divided by A dash B dash, so that I can compare equation 1 and equation 2. Comparing equation 1 and equation 2. Then I will get left hand side equations are same. In the right hand side, BC divided by B dash C. In second equation, right hand side is that is equal to CF divided by B dash F. But here in this diagram, instead of B dash F, see here, instead of B dash F, I can write CB dash minus CF. Right? We know that B dash F is equal to CB dash minus CF. So I can substitute here. So CF divided by, instead of B dash F, I can write CB dash minus CF. Correct? So that this equation become BC by B dash C is equal to CF divided by CB dash minus CF. Now I am going to apply the Cartesian sign convention rule here. Okay, by applying Cartesian sign convention. See here, the distance BC is nothing but object distance U. So I can write BC is equal to U. But by applying Cartesian sign convention, the distance, object distance, see here, we are always taking the distance from optical center. The distance from optical center to object, that distance is opposite to that of incident ray of light. So that object distance is here negative. BC is equal to minus U. You already studied about Cartesian sign convention, right? And the distance B dash C means it is the distance from optical center to the image, and this distance is same as the direction of the incident ray of light, so that that distance is positive. So B dash C I can write it plus B. And here CF is nothing but it is the distance from optical center to the focus. Here also distance is the same as that of the incident ray of light, so that here also the distance is positive. So I can write it CF is equal to plus F. After substituting this all to the equation number 3, I am going to take this equation 3. So after applying after substituting these all distances to the equation number 3, I can write equation number 3 as, then equation 3 becomes BC is nothing but minus U divided by B dash C is nothing but plus B, that is equal to CF is F plus F divided by CB dash or B dash is B minus CF. CF is F minus F. After substitution, we will get the equation like this. Now by cross multiplication, we will get minus U into V minus F. Here cross multiplication, that is equal to VF. Here multiply inside, then we will get minus UV plus UF, that is equal to VF. This much we will get. Now what I am going to do here is, I am dividing this equation throughout by UVF. Then what we will get? Let's see. Dividing throughout by UVF. Dividing throughout by UVF, we will get here minus 1 by F. Okay, here U will get cancelled. In a denominator, F remains by dividing UVF. Here plus by dividing UVF, remaining in a denominator, it remains V. That is equal to, in right hand side, in denominator, it remains U. Correct? By rearranging, what will you get? See here, I am rearranging here. Minus 1 by F is equal to, I am taking 1 by V, that side, that is right hand side. So that I can write 1 by U minus 1 by V. So minus 1 by F is equal to 1 by U minus 1 by V I will get. Again, by changing the signs, finally I will get 1 by F is equal to 1 by F is equal to 1 by V minus 1 by U. This is the final equation I will get. 1 by F is equal to 1 by V minus 1 by U. And this equation is called as a thin lens formula. Thin lens formula. And this equation also applicable for the concave lens also. And it is also applicable for the convex lens also. In both the lenses, this thin lens formula is applicable. That formula is nothing but 1 by F is equal to 1 by U minus, 1 by V minus 1 by U. 1 by F is equal to 1 by V minus 1 by U. So this equation gives the relation between the object distance, image distance and focal length. So that is about the thin lens